Okay, so this is the last week before the break. So this is week 9. Next week is the break, and then the week after is week 10, but that for us that'll also be a break because the Monday of week 10 is a public holiday. It's Labor Day, so we won't have a lecture in week 10, and actually we won't have the lab sessions in week 10 either. So the lab sessions this week will go ahead as usual, Wednesday and Thursday, but week 10 will actually be the non-teaching week for this course. So I'm not sure if that's what's officially in the UNSW timetable, but because of the public holiday, that's essentially what's going to happen. So week 10 will be the non-teaching week. So after today, the next lecture will be Monday of week 11. So 11, 12, and 13. So probably we will have a lecture in week 13. So that might not be in the official timetable, but we think there'll be a review lecture in week 13, and we have arranged for it to be recorded. Yeah. And remember, assignment 2 is due this Sunday. Now, I just had a consultation with some of the tutors, so I know there's been a couple of technical questions asked on the forums. We will endeavour to try to get those answered in the next couple of days and get that sorted out. So Alex Long is up in Queensland this week, but he's in touch by email, and I've been speaking with Adrian and Xue Feng. So we'll try to get that sorted out, and then assignment 3 will be released probably next Monday, just after the submission deadline for assignment 2, and it'll probably be due at the end of week 12. Assignment 3 will involve doing some deep Q learning on one of the simple OpenAI gym tasks. Okay, so today we're going to talk about Boltzmann machines. So this kind of moves into the unsupervised learning. So remember, we did supervised learning and then reinforcement learning. So probably for most of the rest of the course, we'll be talking about unsupervised learning and models arising out of unsupervised learning. So today we're going to talk about Hopfield networks and then Boltzmann machines and restricted Boltzmann machines and deep Boltzmann machines. And if we have time, a little bit about autoencoders. And then after the break, we'll talk in more detail about autoencoders and variational autoencoders, and then we'll move on to generative adversarial networks and other kinds of adversarial training. And that'll be probably round out the course. Okay, so this story kind of starts with the idea of content addressable memory. So people sort of started to get interested in modeling this in the 1980s. So humans have an ability to retrieve something from memory when presented with only part of it. So there are examples. If you've been to high school in a English-speaking country, you've probably learned famous quotations from Shakespeare or Julius Caesar. So if I say to be or not to be, you can immediately complete that by saying to be or not to be, that is the question. This is from Hamlet's soliloquy. And if I've come from some other culture, there would be equally famous quotes from other cultures. I came, I saw, I conquered. That was what Julius Caesar said about the Gauls, Veni, Vidi, Vici, and so on. Now, that, of course, that's to do with language, but also objects. If we see half an object, we can often imagine the other half. So if an object is occluded, and we only see part of it, we can still recognize what the object is, and we can probably visualize what the other half would look like if it were visible. And so as I said, in the 1980s, people started to have the idea of whether we could reproduce this in neural networks. So at this stage, it wasn't about generating novel images, but simply storing a fixed set of images and retrieving them. So the idea is you have a fixed number of images. We want to somehow store them into a neural network. And then if we're presented with an occluded form of the image, so in this case, these three images on the right are images that have been stored into a neural network. And then if you corrupt, let's say you start with one of these images and corrupt it by adding a bunch of noise, the network should be able to denoise that and reconstruct the original image. Or if we're presented with just the left half of the image, we should be able to reconstruct the entire image. And in this case, we're presented with just one corner of the image, and it reconstructs the rest of the image. So this is this is the idea, was this auto-associative memory. And we try to do this with what's called an energy-based model. So we imagine that each pixel in these images is a kind of neuron, and the neuron can have a value of +1 or -1. So -1 is black, +1 is white, and we imagine that there's connections between each pair of neurons, and we define some sort of energy function in such a way that the local minima of this energy function are the images that have been stored. So if we happen to put in one of the stored images, then it corresponds to a minimum of this energy function. And it's we're not interested in the global minimum here, but local minima. We have several local minima all corresponding to images, right? So these three images would all be local minima for the same energy function. And then, so if this energy function is defined, then if we start with if this represents a corrupted image, we could hope to sort of make incremental changes to that image to decrease that energy function and eventually reconstruct the closest stored image. Now, this relates to something in artificial intelligence called constraint satisfaction problems. And those of you who took my course last semester, we went into a lot more detail about this. We looked at backtracking, tree search, and other ways of solving constraint satisfaction problems. Here we're just going to look at the very small part that's relevant. So this is an example of a classic constraint satisfaction problem. You've got an n by n chessboard, and you want to put n queens. This is called the n queens problem. You've got to put n queens on the chessboard in such a way that no two queens attack each other. So that means you have exactly one queen on each row, exactly one queen on each on each column. And then the diagonals, you can't have two queens on the same diagonal. So if you look carefully at this image, there's no situation where two queens are attacking each other diagonally. Now, okay, so one way to formulate this is to say, well, we know there's exactly one queen on each column, so we're not going to even consider possibilities of two queens on the same column. All we have to do is for each column, we have to assign a row for the queen on that column. Now, as I said, there's different kinds of algorithms for solving this type of problem, but the one we're interested in is what's called local search. So you start with just a random configuration. You assign a random row to each queen, so that'll violate a whole lot of constraints, but then we kind of move the queens one by one, and by successive moves hope to get to a situation where we're not violating any constraints. So to a little bit more detail about this, so we select we start with the current configuration. We select one of the columns at random. We select one of the queens at random, and we select a queen that is violating some constraints. So that queen in the corner is attacking another queen diagonally. And then we consider all of the places we could move it, and we look at how many constraints it would violate in each location. So if we moved it here, it would violate one constraint because it would be on the same row as that queen. If we moved it here, it would actually be attacking 3 other queens, this one, and this one. So we calculate that for each row, and we try to pick one that'll violate the minimum number of constraints, which is 1 in this case. And then after that, then we may pick some other, we may pick this queen, which violates one constraint, and we look at the place we can move it, and we've discovered that if we move it down here, it'll violate no constraints because it won't attack any other queens. Okay, so this is a general method for solving trying to solve these constraint satisfaction problems. It's called hill climbing by min conflicts. So I think we discussed this earlier in the course, but when we call it hill climbing, it suggests the idea that this is some sort of fitness and that higher values are better. So we're trying to climb up to the top of that hill. But if we think about it in terms of minimizing the number of constraint violations, it's more natural to turn this image upside down and think that we're actually trying to, if this axis is the number of violated constraints, we want to minimize that. And so we still call it hill climbing, but actually what we really want to do is climb down into a deep valley rather than climb up a hill. So it's a bit annoying to have these conflicting terminologies, but as long as you're used to kind of this image and its inversion, it doesn't cause too many problems. And now there's this issue about local versus global minima. So in this this hill climbing thing goes always to a local minimum, right? And for this associative recall, we don't necessarily go to the global minimum because we really want to just go to the closest stored image, not necessarily, even if some other image has a lower energy, right? And then, right. So in this case, in the n queens thing, this vertical axis is always the number of constraints. In the Hopfield network, it's not the number of constraints, it's some energy function that we're constructing, but in both cases, we want to reduce it rather than, we want to minimize it rather than maximizing it. Okay. So how can we view this, image thing as being an energy, a constraint satisfaction problem or an energy minimization problem? Well, what we're considering here is the configuration space that we're considering is the set of all black and white images with d pixels. So we fix a certain size for the image, and the number of pixels is d. That's the number of rows times the number of columns is equal to d. And so a configuration X corresponds to an image because we assign to each pixel we assign either +1 or -1. +1 is white and -1 is black. And what we want to do is we want to construct an energy function in such a way that the stored images, or we're given a set of images. I give you a set of images and I say, okay, I want you to design this energy function in such a way that those particular images have very low energy, local minima for that energy function. And so for various reasons inspired by physics, and I'll talk a little in a minute about the Ising model of ferromagnetism, but what we do is we say, okay, well, there's going to be some term that just gets multiplied by each xi, and then there's going to be these terms that involve 2 xi. So there's terms that involve just 1 pixel, and there's terms that involve an interaction between 2 pixels. So there's sort of binary constraints, but it's kind of simplified. In general, we don't have any ternary constraints. We don't have terms in this energy function that involve 3 points. We only have terms that involve 2 points. And so it's kind of a quadratic energy function. So that sort of makes it manageable in some sense. Now, how are we going to choose these Wij's? Well, so for this, in general, we could have this second part, which is the sum of bi times xi. In practice, we often ignore that and just set bi equal to 0. Now, in terms of these Wij's, well, what we want to do is, if we look at this set of images that we've been given, and for any 2 pixels xi and xj, we ask ourselves, well, if we look in these particular images, do those 2 pixels tend to have the same color, or do they tend to have opposite color? So if the 2 pixels involved tend to have the same color in those stored images, then we want Wij to be positive. But if those 2 pixels tend to have opposite color, then we want Wij to be negative. And this is what makes this energy function be low for the stored images, because if xi and xj tend to have the same color, then you'll have xi times xj will be +1, and Wij is a positive number, and there's a negative sign there, so this reduces the energy. But if xi and xj tend to be opposite in color, then xi times xj will be -1. You have a Wij that's negative, so when you multiply -1 by the Wij, you get something positive, and again, that reduces the energy. So this is what this is about. So if you go back to this particular example here, let's say, this pixel and that pixel, like if you look at the pixel here and the pixel here, in all 3 images, they tend to be the same color. So that would have a positive Wij, but if you look at, say, this pixel compared to that pixel, well, here it's black, white, here it's black, white, and here it's black, white. So that's what this is about, and we only had 3 images in this case, but you could have more images. Okay. Now, once we've assigned those Wij's, right, so it's just the same thing sort of repeated, but without explicitly talking about images. So a configuration consists of a vector xj for j between 1 and d. So we think of them as neurons in our network. And this is the energy function. So the Wij, we now think of this Wij as if it's this kind of wire that connects those 2 neurons with either a positive or a negative weight. And we normally assume that Wii is 0, so you don't have a neuron connected to itself. And we also assume that Wij is equal to Wji. So these are kind of undirected connections. The connection from one, if it is based on pixels and correlation, then it would be natural for Wij and Wji to be equal. And that's why we have the 1/2 there. Sometimes when we get to the Boltzmann machine, this is sometimes written as the sum, but sometimes we leave out the 1/2. and we write it as the sum for I less than j of that term, which amounts to the same thing. Or here we assume that wij and wji are equal, so each thing gets counted twice in the sum, but then we divide by 2 in order to cancel that out. So this kind of looks like a bit of an electrical circuit, or it kind of looks like a neural network. It is a sort of a neural network, but it's different from the feed-forward neural networks that we've seen in the before in two ways. So first of all, these neurons, the neural networks we looked at before, the activation was allowed to vary continuously. Here, each neuron is forced to have a discrete value. It's either plus or minus 1. It's not allowed to have any value in between. And secondly, the neurons are updated. We don't have a sort of like layered structure where we start with the input and then compute the next layer and the next layer and the next layer. All the neurons are in the same layer, but they're updated either synchronously or asynchronously. So we pick a random neuron and update it, and then we pick another random neuron and update it, and we just kind of proceed in this way. And the update of that neuron, we always update a neuron in a way that will try to reduce the energy based on its connections with neighboring neurons. So this is specifically what happens. We start with an initial state x, and then we repeatedly try to flip neurons one at a time in order to try to reach a lower energy state. And so what we do is we look at we pick a particular neuron xi, and then we look at all the other neurons xj. We only need to look at the neurons j for which wij is not 0. But sometimes it happens that almost all of the weights are non-zero, right? So that's why we talk about the neighboring neurons. And so think about this for a second. So what we want to do is we want to reduce this error function, but we're only allowed to change that particular node xi. We're not allowed to change anything else. So what we have to do is look at this value here. This energy function is it's a sum of terms that don't involve xi plus xi times this value here, the sum over j of wijxj plus bi, right? So we compute, this is the factor by which xi is multiplied in that expression, and so we calculate this, and if this is positive, then it would be best for xi to be plus 1, because when xi is multiplied by this, we get a term that's positive, but then because of the minus sign, that gives us a lower energy. If this expression is negative, then it's better for xi to be minus 1 for the same reason. We get minus 1 times a negative number in the brackets, but then again a negative, so again the energy gets reduced. So the way it works is we say, okay, if we think about it in terms of the pixels, we have a particular image, we randomly select a pixel, and then we ask ourselves, okay, if I were to change the value of this pixel, would it reduce the energy? And if it does, then I change it. If it doesn't, then I keep it as it currently is. And there's some situations where changing the pixel wouldn't make any difference. So just for completeness, we say, all right, well, in that case, we'll just keep whatever value we had before, so that we get a stable state for these images. We don't get little pixels just randomly flipping back and forth. And so this is exactly, I mean, this is basically the same kind of thing as hill climbing by min conflicts, but instead of min conflicts, it's all about reducing the energy. Every time we change a pixel, we only change a pixel if it's reducing the energy. And so eventually we must get to a state where it's impossible for us to change any pixel. Eventually we must reach a state where no matter which pixel we change, it would increase the energy. So by definition, that's a local minimum. Any questions about this? Yeah.
Correct me if I'm wrong, but it seems like the numbers would blow up really fast here, right? Like you get 100 by 100 image.
Yeah.
You'd have 100 to the power of 4 weights, so like 100 million.
No.
Or am I
100 squared. 100 squared. Oh, sorry, okay. Yeah, sorry, you're right. So if it's 100 by 100 image, yes, it would be 100, you're right, yeah, 100 to the 4, which is, how many is that? 100 million, is it? Yeah, okay, very good question. So let me repeat that. So if the image is 100 by 100, that means there's 10,000 pixels, 10,000 neurons, and the number of weights is proportional to the square of the, it's actually, yeah, if there's, it's the square, it's proportional to the square, or maybe if there's d pixels, then the number of connections is d squared over 2. So you're right, it's 50 million. Yeah. Okay. So that is big, but, okay, yeah. But on the other hand, if you look at things we were looking at, like ImageNet and so on, they have even more. They have 60 million or something. So, well, 200 and, okay, yeah, 247, yeah. You're right. I mean, I guess this, okay, so there's two things to point out. Yeah, so it's a very good point you raise. So these models that I'm talking about today are actually, in a way, they're more of historical interest, because the techniques we'll talk about after the break actually kind of do the same thing in a more powerful way, let's say, or a better way, or produce better images. So the main reason we look at this material is just it kind of builds up the initial ideas from which the other models are built. I guess this would normally be applied to sort of, well, I was going to say lower resolution images, although it's a good question. What's the resolution, do you think, of these images? Yeah, probably about 100 by 100, yeah. So we normally think of this in relation to smaller images like MNIST, which is 32 by 32, or possibly like 64 by 64. Yeah, usually not larger than that. Yeah, it's a very good question. Yeah. Okay, so now let me be a bit more specific about how these images are stored. So we have a set of images. So I'm trying to follow the textbook as closely as possible here, or other resources. So we use D for the number of neurons, and we use P for the number of patterns being stored into the network. So P is the number of stored images. And So we write the index, in order to distinguish the index of the image as opposed to the pixel, we write it as a superscript rather than a subscript, and we put it in round brackets. So xk is the kth image to be stored. And so specifically, we set bi equal to 0, and we set wij equal to 1 over d times the sum for k equals 1 to p of xik xjk. Right? So for each pair of pixels, we add up the number of, so this is kind of like a correlation, but it's been slightly scaled according to the number of pixels and the number of images. So I pick 2 pixels in the image, or in the frame as it were, 2 locations in the image, and for each of the stored images I ask, well, are these 2 pixels the same color or a different color? So if they're a different color, I put -1 in the sum, and if they're the same color, I put +1, and I add that up for every stored image, and then in the end I divide the whole thing by the number of, not by the number of images, but by the number of pixels. And so another way to write this is to say, well, let me compute the fraction of images for which the 2 pixels are the same color. And let me call that C. And then wij is equal to -1 plus 2c times p over d. Right? So minus if it's half and half, if the 2 pixels are the same color in half of the images, then wij will be 0. If the 2 pixels are always the same color, then it will be p divided by d. And if the 2 pixels are always the opposite color, then it'll be minus p over d. Okay, and in general, it'll be somewhere in between those two values. And this is sometimes called Hebbian learning. Now, again, these terminologies come from neuroscience. So it's been established. We still don't know all the mechanisms by which learning takes place in the brain, but one process that does go on is called Hebbian learning. That means that if one neuron fires, and let's say, I mean, usually there's a timing involved. If this neuron fires and it's connected to this neuron, and this next neuron fires shortly afterwards, then there's a process that goes on that will actually strengthen the connection between those 2 neurons. This is called Hebbian learning. And so that's what's going on here, that if xi and xj, remember, if we think of these as neurons rather than pixels, then we're sort of imagining if the images are presented one after the other in a random order, if these 2 pixels are the same color, we think of that as like the 2 neurons are firing together, and so we strengthen that connection. If they're opposite colors, then we make it a negative connection. Now, one interesting consequence of all this, if we make this particular choice for bi and wij, one consequence is that if one image is a stable attractor for this, then actually the negative of that image will also be a stable attractor. So if I didn't, actually, I wonder if I can, oh, there we go. Yeah, so these images would also be stable attractors. So if a black spider on a white background is stable, then a white spider on a black background, and white beer bottles on a black background and a white dog on a black background will also be stable attractor. So there's this sort of slightly odd symmetry about this which we may not want, and that's one of the reasons we move on from the Hopfield network to the Boltzmann machine, which we'll talk about later. But for the Hopfield network, it does have this curious property. Okay, now once the images are stored, then, so how do we analyze this? You know, if that's the choice we make for the Wij, then for any item, for any stored item, then we can ask ourselves, okay, if I give you a stored item, is it actually going to be a local minimum? Is it going to be a stable state for that network or not? Well, if I pick a particular stored item XL, then remember the jth pixel. If I start with that image, and I want to pick a pixel and decide whether it's going to be flipped or not, well, the jth pixel in image number L, there's no BI, so I just calculate this particular sum, and if that sum is positive, then the pixel will be set to +1, and if that sum is negative, the pixel will be set to -1. But if I plug in the formula for Wij, it turns out to be this. So this is the sum over all the pixels and the sum over all the patterns of xik, xjk, xjl. And if you look at if you look at the terms, so we started with a particular image L, and then we're summing over all images K. Now, if K is equal to, somewhere in this sum is the term where K is equal to L. Now, if K is equal to L, then xjk, xjl will be equal to 1, right? If K is equal to L, this number is either +1 or -1, and it gets squared, so that's equal to 1. And so you get the sum for j equals 1 to d of xik, but this part doesn't depend on j, and so you're summing the same thing up d times, and then you're dividing by d, so that just gives you xil, the current value of that pixel in that image, and then the other terms. Well, it's the same sum as this, except we've excluded the case where k is equal to L. So this is the sum for k not equal to L. And so we can use this to analyze this Hopfield network. So the first term is the one that we like, because this is the actual value of that pixel, but this thing here is called the crosstalk term, because this is the term that is caused by interference with all the other stored images, you know. And so whether this thing is a stable state depends on the size of that crosstalk term. So if that if the size of this term, so remember this xil is either +1 or -1, yes?
When you say interference with other stored items, is it multiple items, or just like, is it like how is it?
It's multiple items. So let's say, so in the example I showed you, we only stored 3 images, right? But we might store 20 images, right? Yeah. Each image is getting interfered by 19 other images. That's exactly right. Yeah. Now, so if this so this part here is either plus or minus 1. And then the question is, what about this term? Now, if the absolute value of this term is less than 1, then when we combine these two things together, it'll have the same sign as this, right? If this is minus 1 and then we add something whose absolute value is less than 1, the answer will be negative. And if this is plus 1 and we add something whose absolute value is less than 1, then we'll get something positive. So in that case, this pixel will, when we decide whether to flip this pixel, we'll decide to keep it the value it currently has. So this is the value that it currently has, and then we're adding something that doesn't change the sign. So with the update, we'll be saying, okay, we're going to keep the value that we currently have. Yeah. Also, if this thing is bigger but happens to have the same sign as this, then it'll be the same, right? If this is plus 1 and this happens to be positive, then the whole thing will still be positive, right? Now, what's the likelihood of this? What's the likelihood that this term here will have an absolute value less than 1? Well, this is where, it depends on what those other images are, but we could make the assumption that these terms are all random, let's say. So these three terms here, each one is either plus or minus 1. When we multiply them together, we get plus or minus 1. So we can get an idea by thinking of this as coin tosses. So we talked earlier in the course about if you toss a coin 10,000 times, what's the likelihood? If you toss a coin 10,000 times, you expect on average you expect to get 5,000 heads and 5,000 tails, and if you draw a distribution of how many heads you expect, it's a Gaussian distribution, so the mean is 5,000, and I think the standard deviation was 50, right? So the standard deviation scales according to the square root of the number of coin tosses. So we've got the same idea here. If we assume that these numbers, like, they may not really be independent, but if we assume that they are independent, we're just adding up. The number of things we're adding up is d times p minus 1. So we're tossing a coin. We could think of it as tossing a coin n times, where n is d times p minus 1. And then you can ask yourself, well, what's the likelihood that this is sufficient? So the mean is 0 in this case, because we're adding plus 1 for heads and minus 1 for tails. So on average, we expect to get an answer of 0, but then there's a certain standard deviation, and the standard deviation is going to be proportional to the square root of d times p minus 1. But then after we do all that summing, we divide by d. So the final answer is going to be proportional to the square root of p minus 1 divided by the square root of d. Right? So I won't go through all the mathematics, but if you go through all this in detail, the likelihood of that crosstalk term, the probability of that crosstalk term being bigger than 1 is, you can calculate it. It depends on the relationship between, it depends actually on the ratio between P and D. So remember, P is the number of images we're storing, and D is the number of pixels. And the size of this term roughly is the square root of P minus 1 over D, right? So if it turns out that if if P divided by D is less than, there's a certain magic number here. If P divided by D is less than 0.138, then we can have a reasonable expectation that the patterns can be stored and retrieved successfully. Right? So the number of patterns we can store depends on the number of neurons. If we're just storing 10 by 10 images, then the number of pixels is 100, so we should be able to store 14 images, 13 images. If the images are 32 by 32, that's 1,000 pixels, and so we should be able to store 138 images successfully. So if we try to store more images than that, then what happens is you get these sort of spurious states. So the images that very likely the images that you store will be local minima, but then there'll be additional other local minima that are somehow a mix of different images that you've put in. So if you might have an image that's a mix between a spider and a beer bottle or something like that. You get these sort of spurious states. Okay, now I just I was looking on YouTube. I found a very simple, small example of this. Let me just find this. Yeah. Might make it a little bit more tangible. Oops, not preview. So you can see here they've got, how many pixels have they got? It's just 5 by 5. So they've got 25 neurons and they've stored these 3 patterns. And they start with an image like this, and then they run it, and it stabilizes to one of the stored patterns. Here, they're trying to. I kind of like this. I think he was trying to create the second pattern, but he was trying to recreate the second pattern, but it ended up recreating the first pattern. So sometimes it depends on the order in which the nodes are updated, which pattern you end up with. Actually, sorry, let's just look a bit more in detail at this. When he started it running, how close is it to this pattern? It's got one. How many pixels differ from this pattern? 1, 2, 3, 4, 5, 6. And what about this pattern? 1, 2, 3, 4, 5, 6, 7. Right, so it's kind of almost equally close between the two of them. So I think then he goes through and tries to create something that's definitely closer to the second pattern. And it gets recreated, yeah. So it's a sort of simple demonstration here. Okay, so any questions about this? Okay, so what can we say about this? Well, the Hopfield network, as I say, it was used to store specific items and then retrieve those items, right? Now, what we really want to do is generate new items. So what we would really like is I give you a bunch of images of digits or bedrooms or faces, and we want the network to generate new images which look kind of, are similar in style to the images that I provided, but not quite the same. We don't want it to retrieve exactly one of the faces that we put in there. We want it to actually create a new face which looks like a face but doesn't look like any specific existing face. That's what we want, is a generative model. Okay? So I'm going to describe a series of attempts over the years. So what we're going to describe today is kind of early attempts at this from like 1997 ranging up to about 2008 or so, and then afterwards we'll look at some more modern techniques. Okay, but this is the first attempt. It's called the Boltzmann machine, and later attempts is kind of built on top of this. Now this is, I should say, like, both of these models are inspired to some extent by this thing in physics called the Ising model of ferromagnetism. So I just sort of mentioned this in passing. So this is, if you've got an iron bar, it can be magnetized, it can be unmagnetized, it can be magnetized with north at one end and south at the other, or it can be magnetized in the other way with south and north reversed. And if you kind of look into the physics of this, there's all these little ions, ION, in this bar, which are arranged in a lattice, and there's a force, and each ion has a spin, and the spin can either be up or down. So some of them are pointing up and some of them are pointing down, and these things are sort of randomly flipping. There's this process going on where a node randomly flips based on its neighbors. So there's a force, if you look at, there's a force that kind of tries to get each ion to be in alignment with its nearest neighbors. So in the two-dimensional case here, each ion has 4 neighbors, and so randomly an ion decides to try to flip itself. Now, if you look at a case like this has 4 neighbors, and 2 of them are pointing down and 2 of them are pointing up. So it'll have an equal chance of being up or down. But if you look at this ion here, of its 4 neighbors, 3 of them are pointing up and 1 is pointing down. So when this guy decides to try to flip, there's going to be a higher probability of it flipping up, of it going up rather than down. And the probability is actually dependent on the temperature. So if the temperature is very high, it's just going to have an even chance. It's just going to be totally random. It'll have an even chance of coming up or down. If the temperature is very low, then it has a very high likelihood of going up. And so the way you create a magnet is actually by a process of annealing. Annealing, strictly speaking, annealing means starting at a high temperature and gradually cooling something down. And so if you cool it if you reduce the temperature too quickly, you'll end up with a situation where it's just all kind of random and it won't be magnetized. But if you cool it very, very slowly, it will actually end up in a state where the vast majority of ions are pointing in a particular direction. And this actual simulated annealing is a bit outside this course, but these models are related to this. So if you think about this, so this, you could see this Ising model is very closely related to this image thing we were talking about, except that each pixel is only connected to the nearest neighbors, and there's a force that encourages it to be similar to its neighbors, so that if they're black, it'll try to become black, and if they're white, it'll try to become black. So for that model, the only two stable states are the image that's fully black and the image that's fully white. But then there are some sort of local minima as well. So the idea when you do that simulated annealing, when the temperature is very high, the state is just roaming randomly over the whole state space. As you lower the temperature, it still moves randomly, but it's spending more time in the regions that have lower energy. And if you cool it slowly enough, eventually it'll end up in this global minimum. Okay, so that's the sort of physics behind this. All right, so in detail, though, the Boltzmann machine, it's very similar to the Hopfield network, but it differs in certain crucial ways, right? So the energy function looks exactly the same as for the Hopfield network. That expression is identical to the previous expression. As I said, instead of writing the sum over all I and j and then having it, I'm just writing the sum for I less than j, right? But it's actually exactly the same thing. So the energy function is the same. So how is it different? Well, first of all, these neurons take on the values of 0 and 1 instead of -1 and +1. So we don't like that symmetry. That symmetry involving the black on white and white on black, we don't really want that. So one of the things we're going to apply this to is digits. You know, maybe it's better. Maybe it's good if I actually show you the video first, and then we look at the details afterwards. So this is a this is a Boltzmann machine that's being trained to generate digits. So it's this is using that famous MNIST data set that we looked at with homework 1, and this is what's happening while it's training. So I'll get into the details of this later, but it's being presented with these images one at a time. And then after, this is in the early stages of training, and this here is in the later stages of training. Sorry, I've got too many windows here. Where's my YouTube? This is in the later stages of training, and well, it's we'll talk more about this. We'll look at more of this in detail. These hidden nodes are actually have kind of become a bit like features, but this is the thing where it's actually generating. So it's sort of dreaming different digits, and I'm not sure whether this is constrained to create only the digit 7, but I think it is. So here it's creating phantom digits of O, and so on. So you could see this generative process. Now, as I said, like this goes back. This is from 2006. This, you know, by modern standards, this is kind of hokey. We can do a much better job than this, but this is like the early attempts to do generation. Okay, so. Okay, so one of the reasons, it's a bit, this 0 and 1 instead of -1 and +1, the reasons for this are a little bit subtle, but one of the reasons is if we stuck with the +1 and -1, we'd have, with the Hopfield network, we had this thing that if a white on black 7 is a stable state, then a black on white 7 would be equally stable. And so the network would be a bit annoying. It would kind of, over a long period of time, it would produce white on black digits and then switch over to black on white and back again, and that's kind of annoys us. We don't really want that. We want to just fix, okay, we want digits that are black on white, and we'd stick with that. So it's good to break this symmetry. But it's interesting the way this works. So what that means is this term only has an effect if xi. So we think of these, we don't think of these as black and white anymore. Well, we think of them as like features, that can be present or absent. And because of this term, it's only if two features are both present that they contribute to this energy function. If either of xi or xj is 0, then this term disappears. Okay, the second difference, we're going to use this to generate new states rather than retrieving stored states. And the third thing, the update is not deterministic, but it's stochastic. Okay, so this is where this is something that's related to simulated annealing, but we're not going to quite do simulated annealing. So, okay, so if we go back to that Ising model, that Ising model with all these ions could be plus or minus, up or down. If you fix a particular temperature and then you let the system, if you fix a particular temperature and then you allow neurons to randomly flip over time, what actually happens is that the probability of being in a particular state is given by this equation, e to the minus energy of x over t divided by z, where z is a normalizing constant. This is known as Boltzmann's equation because Boltzmann was the physicist who first described this. And it's sort of a little bit similar to softmax. If you remember with softmax, we had the probability was proportional to we were selecting between 10 different outputs, and we said that we interpreted the probability was proportional to e to the power of one output. This is very similar to that, except that we've got this negative sign. We want to have a low energy rather than a high output, so we treat the lower the energy, the bigger the probability. And in general, we also have this kind of temperature. And so, okay, so how should I put this? Like, in a way, we might like to do simulated annealing, but how do we sample from this distribution? Well, remember, we're just changing one neuron at a time. And so it's kind of impossible to compute this distribution analytically because we can't really compute this partition function. But if we just change one neuron at a time, then we can do something computationally tractable. So what we do is we say, okay, well, I have a particular image X of one of these phantom digits, and I just pick a particular pixel, and I'm going to keep everything else the same, and I just think about changing this one pixel. So I'm not changing the whole thing, I'm just changing one pixel at a time. And then I say, all right, well, if I were to change, let's say this pixel currently is equal to 1, and I'm thinking about changing it to 0, but leave everything else fixed, would the energy increase or decrease? So I try to calculate the difference in energy. What's the energy of the current state, and what would be the new energy if I change this to a 0? So the current state is x, the new state would be x prime, and I'm looking at I want to look at the difference between the energy of x and the energy of x prime, and I can calculate this, because remember, this is very similar to the Hopfield network. It's the same equation. So by just looking at this neuron and how it's connected to all the other neurons, I can figure out what would be the difference in energy if I make the change. And then it follows from this equation, so I can't calculate the absolute probability of any particular state, but I can calculate the conditional probability of this neuron. If I can calculate the conditional probability determined by this probability distribution, I say, okay, if I keep everything else the same, what's the probability of this thing being 0 or 1, right? And it turns out that because it's proportional to this delta t, right? If I consider just if I just consider two states, I'm only considering two states, x and x prime, right? These two states are almost the same, except one pixel is different, one neuron is different, and I'm asking myself, well, what's the relative probability of x and x prime? Well, it must be proportional to the difference in energy between x and x prime, right? So I don't know what either of these probabilities is absolutely, but I know that one of them is equal to the other multiplied by e to the minus delta e over t. And so, therefore, the conditional probability is probability of x divided by probability of x. This is why we went through this thing with Bayes' theorem and so on earlier in the course. So we get to this, we have a better understanding. So the probability of, if everything else is fixed, the probability of xi being 1 will be p of x divided by p of x plus p of x prime, which is equal to this, right, relatively speaking. And you will recognize this as the formula for the sigmoid function, right? And the probability of it being 0 is going to be 1 minus that, right? So this tells us what the update function should be for the Boltzmann machine. So it operates, it operates similarly to the Hopfield network, except that there's some randomness in the neuron updates, right? So if you think, in both cases, we repeatedly choose one neuron and decide whether to flip it or not. And if we were to flip it, it would change the energy function from x to x, it would change the state from x to x prime. We calculate the change in energy. So with the Hopfield network, we were very strict about this. If changing it reduces the energy, then we change. If changing it doesn't reduce the energy, we stay where we are. So it was very, very fixed. Now with the Boltzmann machine, we decide randomly whether to change or not based on this probability. So what happens is we generate a random number, but we calculate this thing on the right-hand side. We generate a random number between 0 and 1. If the random number we generated is less than this, then we change, and if it isn't, then we stay where we are. All right, this will be the last slide, and then we'll take a 10-minute break. So the probability of xi going to 1 will be this number here, assuming it's currently equal to 1, yeah, so the probability of it's going to 1 will be 1 over 1 plus e to the minus that. So the sigmoid of this number here. Okay, so let's just look at the properties of this. So it turns out if we repeat this process many times, eventually we'll be obtaining a sample from this Boltzmann distribution. If we flip one neuron and then another neuron and then another neuron, and we just keep going, over time we're going to be randomly sampling from the Boltzmann distribution, and this is what was happening in that video. You notice there was always sort of small changes. There was only one neuron changing at a time, but over time eventually it goes through all digits that the network allows, kind of thing. Now, let's think about this temperature parameter. So as t goes to infinity, dividing by infinity is the same as multiplying by 0. So e to the minus 0 is 1. So the probability becomes 1 over 1 plus 1, which is a half. So when the temperature is very high, I'm just picking a node and I'm picking a neuron and randomly, with probability 1/2, I'm setting it to either 0 or 1. So it's just a totally random process, right? So I'm just getting a uniform distribution. Now, as t goes to 0, dividing by 0 is the same as multiplying by infinity, and e to the minus infinity is 0. So in that case, it behaves like the Hopfield network. When the temperature is very close to 0, you only change if it's going to reduce the energy, and so you're guaranteed to get to a local minimum in the energy. Now, technically, so often what happens is we just keep the temperature fixed, and we just keep t equal to 1 is what usually happens. And now technically, this is the term annealing. Sometimes we start with a high temperature and gradually reduce it. Strictly speaking, that's what annealing is. If the temperature is fixed, strictly speaking, we shouldn't call it annealing. We should call it the Metropolis algorithm, because Metropolis, again, was one of these physicists who described this. But sometimes we call it annealing at constant temperature, which doesn't really make sense. But sometimes we would call it that. Yeah. So usually we just have t fixed. And you've already seen the video that gives you some idea what happens. Okay. Any questions about this? Good. Okay, we'll take a 10-minute break. When we come back, I'll tell you about restricted Boltzmann machines and deep Boltzmann machines, and maybe a little bit about autoencoders, and then that'll be the end of today. Okay, so the Boltz. Okay, so this Boltzmann machine really dates back to the late 1980s, but the problem with it is that this method is actually very slow to converge. And so eventually people tried to come up with I think it was probably Jeff Hinton who did this, that tried to come up with a simpler well, it's called a restricted Boltzmann machine. So it's simpler in some sense, but it converges faster. And the trick involves splitting the right, so with the original Boltzmann machine, everything was connected to everything. So if we're trying to look at those digits, you know, every pixel interacts with every other pixel, and we can do this this iterative update as I described it, but you need to do many updates in order to get a reasonable sample of all the different things that the network can produce from that distribution. Okay, so what they decided is, okay, well, what we're going to do is those pixels that we can see on the screen, we treat them as being visible units, and then we introduce a new set of units that are called hidden units. And so these are the visible units, which are the actual pixels. These here are hidden units, which are sort of in the background. We can't actually see them, but they are there. They're like latent variables. Well, we could have done that and had the full Boltzmann machine. You know, we could have had all the visible units connected to each other and all the hidden units and the visible and hidden connected to each other. And we could do the update here, but only show the visible units on the screen. But again, that would be very slow. So instead, what we do is we have a rule that says that all the visible units are connected to all the hidden units, but the hidden units are not connected to each other and the visible units are not connected to each other. So that's why it's called a restricted Boltzmann machine, because the connectivity is restricted. But the update becomes much faster because you can update all that. So so the way this works is I have particular values for the hidden nodes, and then I want to calculate a new set of values for I have a particular set of values for the visible nodes, and I keep them fixed, and then I want to choose values for the hidden nodes. Well, each hidden node depends on all the visible nodes, but the hidden nodes don't depend on each other. The hidden nodes are not connected to each other, so I can update all the hidden nodes at once because they're conditionally independent given the visible nodes. So I clamp the visible nodes, or I keep the visible nodes fixed and I change all the hidden nodes. And then at the next step, I keep all the hidden nodes fixed and I change all the visible nodes. So this is the way this restricted Boltzmann machine works. This is back and forth between the visible nodes and the hidden nodes. Okay, so those inputs, again, are binary vectors. They're either 0 or 1. And then we have the visible layer V and the hidden layer H. There's no connections between two visible nodes and no connections between two hidden nodes. And then the energy function is the same as before, but we write it in this way because we've got this split before we had this xi and xj, because we now have this division between visible and hidden nodes, we write it like this. So if the constant term for visible node VI is the bias term is written as BI, and for HJ it's written as CJ, and then we only have interactions between a visible node and a hidden node, so we write this as the sum over I and j of VI times Wij times Hj. So this is the same equation as before, except that we've adapted it to take account of the fact that we have this structure, we have this division between hidden and visible nodes, and the connections are only between the hidden and visible layer and not inside the layer. And we want to train this to maximize the expected log probability of the data that we're given. Okay, so this is quite similar to what we saw before with the sigmoid, but it's just the notation. Because everything's being updated a whole layer is being updated at once, we have a kind of slightly more involved notation. So, okay, so we want, let's say we fix the visible nodes, and then we want to generate new values for the hidden nodes. So the conditional probability of the hidden nodes conditioned on the current values of the visible nodes is the combined probability of V and H divided by the probability of V. That's 1 over the probability of V times this exponential. I'm not sure. Yeah, there was a minus sign here. So the Boltzmann distribution, we have e to the minus energy divided by temperature. So we've gotten rid of the temperature here. We just assume the temperature is always equal to 1. And the two minus signs have cancelled each other out. So the probability, the joint probability of V and H is proportional to E to the energy of that particular configuration of V and H. And so we have this Z is meant to be the partition function for the whole distribution, and this is probability of V. But remember, V is being kept fixed and we're only changing H. So these two are both just constants that we don't know these constants and we can't do anything about them. So we just sort of put them together as a new constant, which is Z prime. And the other thing, we can't do anything about this term here because that only depends on V and we're updating H. So we absorb this also into that constant. So we absorb all of that into this new constant. And what we're left with is this. So again, it has the same. This is the beauty of this Boltzmann distribution, is that when you conditionalize it, it still has the same form as e to the power of some energy, but then divided by some new normalizing term. Now, we follow the same logic that we did before. We don't know this Z prime, but for each individual H, we can, for each individual hidden node, we can calculate the conditional probability of that node being 0 or 1 based on the current values of the visible nodes. And we can do that independently for each H, because the H's don't directly interact with each other. They only interact through the visible nodes, and if we keep the visible nodes fixed, they become independent. So they're conditionally independent. And so what this simply says that for each, what this says is that for each component Hj, calculate, all right, so this becomes like a matrix multiplication. You know, if I treat these Wij, if I teach this W as, if I put theseWij's into a matrix, then I'm just taking the transpose of that matrix multiplied by V and extracting out the jth component. You know, this looks like a matrix multiplication. And I'm computing sigma of the, well, this 2h, what's this 2h minus 1? So hj is either 0 or 1. So this 2h minus 1 makes that number there either positive or negative, depending on the value of hj. And then I'm calculating the sigmoid of that. So really, this is just, it look. God, sorry, I don't know. It's this is really just these expressions here. You see how there's a sigmoid and there's a plus or minus. So the 2h minus 1 is just giving us this plus or minus depending on whether this is 0 or 1. And then we're calculating the sigmoid. So you know, this notation is different, but it's really just the same as those previous equations, but we're doing it simultaneously for every hidden node. And then we're multiplying them all together, and that gives us a probability. Yep. Yes. Why are we using Bayes' theorem? Not using Bayes' theorem. What do you mean when you say we're not using Bayes' theorem? Probability of H given V is the probability of, probability of V comma H means the probability of V and H. I think this is the same as Bayes' theorem. What does Bayes' theorem say? Probability of, okay, probability of,
I think it is the same as the probability of,
okay. It's written, you're right, it is written differently. Okay. Okay, the question was that when we discussed Bayes' theorem, it was written as probability of H given V is equal to probability of V given H times probability of H divided by probability of V, right? Okay, so yes, this is a little bit different from that, but the probability of, if this was probability of V given H times probability of H, that's the same as the probability of V and H. Yeah, so that's why we've written it like this. Yeah. Okay, so this is, again, I've copied this notation from section 20.2 of the textbook, but really this is just a fancy way of saying that we apply those equations to all the H's concurrently. If we've got a GPU, we can do that. Okay, any questions about this? Yeah. And you go back and forth. So that's the probability of V given H. And then at the next time step, we fix H and generate a new V. So the equations just look the same, but flipped the other way around. Okay, so this leads to the, so this is called alternating Gibbs sampling. So we start with a particular we start with a particular value of v. Based on that value of v, we generate a value of h. Based on that value of h, we generate a new value of v, and we keep going back and forth. And if we were to do this over and over time, we were randomly sampling from the Boltzmann distribution. And in a sense, this is happening much faster than with the regular. This is actually happening, the time it takes for us to kind of sample from the distribution is much faster than with the full Boltzmann machine, partly because we're updating all of those hidden nodes at once, not just one at a time. So once the thing is trained, this is actually how those fantasies were generated. So when we were looking at those phantom digits appearing on the screen, this is how it was done. You know, hidden. Maybe it's worthwhile to go back and just have a look at this video again, because you can understand now the difference between this hidden and I'll point out this difference between this hidden and visible units. So this is where it's dreaming, and these are actually the hidden units. These are the hidden units, and these are the visible units. Okay, that's nothing. That's just the state we started from, and then we're going back and forth between these two. We're keeping this fixed, regenerating that, then keeping this fixed, regenerating that, back and forth, and this is the result. Okay, then we do some more training, and then we're doing some more generating. So you see, it just happens here that the number of hidden units is, we've arranged the hidden units in a square, but really there's no significance to that square. Those hidden units are all just kind of independent of each other. But you can see, like, this particular set of hidden units, so the hidden units can be 0 or 1 as well, and this particular set of hidden units corresponds to that visible unit, or makes this particular set of visible units more likely. Any questions about that? Okay, so that's after it's trained. This is how we do the generation. But then there's the question about how to train it. Okay, so in the beginning, well, so it's trained I'll tell you the slow way and then the fast way. So the slow way is called contrastive divergence. The fast way is called quick contrastive divergence. So how does this contrastive divergence work? Well, okay, so let's think about this. So you've got a set of real images. You've got a set of real digits from this MNIST database. So we call them positive samples. VK, right? I'm using the same notation that we used for the Hopfield networks. And so we can start with a VK, a real digit, and then based on those visible units, we can sample a hidden vector based on that conditional probability. And then based on that H, we can generate a new set of visible units, so that creates a sort of fake sample. Now, what we want to do is we want to increase. So the original method, you had to go. The original method was to go through this process several times to create a fake sample. So you start with a real sample. You alternate these hidden and visible units several times, and then this gives you some kind of fake sample. And so you have a set of real samples and a set of fake samples, and then what you want to do is you want to increase the probability of the real samples and decrease the probability of the fake samples. Because in the training phase, we don't trust that we start the network with just random weights, and so if we go through this process, we don't trust that it's really creating a good sample. We think it's just creating something that won't look like a digit. So we want to train it to make that one less likely and train it to make the real one more likely. So we want to train the weights to increase the log probability of the real digit and the hidden units that we generated from it, but we want to reduce the likelihood of the fake one. So this is the real one, and that's the hidden unit we generated from it, and then we went through several steps, and eventually we created this fantasy one and created a corresponding hidden unit. So we want to increase the probability of this and decrease the probability of that when we're training. Now, because these weights are linear, the way to do this is to actually, BI gets trained by adding eta times VI minus the real minus the fake sample. These bias weights Cj get updated by adding eta times the real hidden units minus the fake ones, and the weight Wij gets updated by adding this. So this is actually just calculus. Once I tell you that we're updating this log probability, or we're trying to increase this log probability, this just follows from the previous equations. Because the log, remember the log of this exponential is just this quadratic function, and then we're trying to increase this quadratic function. So these updated equations actually become, in a way, they become linear, effectively. Yeah, so it's a bit reminiscent of, this is a bit reminiscent, I mean, it's a totally different context, but this is a little bit reminiscent of word2vec, when we were trying to increase the probability of real words and decrease the probability of fake words. Okay, now, as I say, when people first started to do this, they would have several steps of this process in order to get this fake thing, but it was taking a long time to train this. So then I think it was in 2006, someone in Hinton's group in Toronto realized, well, they said, let's just try to do this in a quicker way. Instead of doing multiple steps, I'm just going to do the minimum number of steps. I'm going to start with a real digit and then generate hidden units, and then from those hidden units I'm going to generate possible visible units, and then from that I'm going to generate possible hidden units. So instead of multiple steps, I just do these few steps, and then I'm going to use this as my negative example and this is my positive example. And it turns out that this gives reasonable results. It's actually this can be compared with negative sampling in this is all kind of analogous to word2vec. This can be compared with a negative sampling from word2vec. So if you remember back to word2vec, the mathematically clean way of doing it would be to do the full softmax, but that wasn't computationally feasible. So then we replaced it with a hierarchical softmax. So the hierarchical softmax is mathematically kosher, and it's also computationally feasible because it's guaranteed to be an actual probability distribution. Then we looked at negative sampling. Negative sampling is not mathematically rigorous in some sense because there isn't a probability distribution that it's based on, but it gives reasonable results in practice. Well, this is the same kind of thing. Because we're only doing these 3 steps, it's not mathematically rigorous. It's not guaranteed to really minimize what we want, but in practice it actually gives good results. And it's sort of one way to think about this, and yeah, so the videos that I showed you were actually sort of based on this. Now, one way to think about it is the following, that you start with a real digit, and you're only doing because you're only doing 2 steps, you're generating something that's quite close to the real digit. So I didn't sort of draw a picture of this, but you imagine you've got real digits that you're using as your positive examples, and then you've got things that are not real digits but are actually quite close to real digits, and you're using those as your negative examples, and you're trying to train you're trying to train your network to produce one and suppress the other. So there is a danger. The thing is, you're only using negative samples that are close by. You're not using negative samples that are far away. So there is a danger that your network might actually produce things that are far away because it's never been trained not to. So that's the sort of danger, but it turns out that in practice that often doesn't happen. Yeah. So again, let's just I keep coming back to this, but we sort of look for different things each time. So this is the this is the early phases of the training, and you notice how these hidden. Okay, so what's actually? Let's look at all the aspects of this. So this is the visible units. So for this training example, we generate some hidden units that are not shown, and then we generate a visible unit from those hidden units, and then from that we generate a hidden unit. So this is what's going on with the training. This is a Hinton diagram showing all the weights. So this is each of these little squares. Each of these little squares corresponds to one hidden unit, and the pixels within the square show the weights between the visible units and that hidden unit. Okay, and this is probably the bias here. So this is what's going on with the training. Now you notice in the early stages of training, these things here look pretty sort of random and crazy, and these all look sort of kind of washed out. But then if we fast forward to the late stages of training, you notice 2 things. First of all, these fake visible units are actually pretty close to digits. And it's also interesting to look at what's happened to these weights. They look much more, well, they look like the features. If you think back to the, if you think back to the hidden features from a feed-forward neural network, this has been done unsupervised, but if you were to train a 2-layer neural network with this number of hidden nodes to predict the class of the digit, if you were to do that, you would probably get hidden unit activations that look quite similar to this. You see, the individual hidden units have specialized in certain parts of the image. This unit here is highly connected to pixels in a certain part of the image. You know, so it actually, so in a totally unsupervised way, it's extracted out features which are similar to what you would see if it was trained supervised. Yeah. Okay, so now just a couple more slides, and then after this I may just go through a few of the exercises from previous weeks and make a couple of comments on them. Right, so this is the Boltzmann machine, the quick. So what I showed you that video is the Boltzmann machine trained by quick contrastive divergence. Now you see the results are okay, but those digits don't really look that convincing. Now the next step was the deep Boltzmann machine. So the way this works is you train one hidden layer in exactly the way that I described, and then you fix the weights here, and you train a second hidden layer to try to recreate the activations in the first. So you use exactly the same method here, but between these two layers. So I put in a digit. I use these feed-forward network. I use these weights here to choose hidden unit activations here. Now remember, these are stochastic, so these values are 0 and 1. It's not quite the same as a feed. If it was just a feed-forward neural network, I would simply add up the weights and put them through the sigmoid. Here, I add up the weights, I put them through the sigmoid, but then that gives me a probability, and then I use that probability to assign either 0 or 1. So these things have to be 0 or 1. And then I use the same algorithm here. I treat these as if they were visible weights and try to create hidden weights here. So the idea here is that you try to create a set of hidden weights that are abstracted away further. And you could do this multiple layers. And what this was used for, one of the things this was used, well, there's two things. So we can then use this architecture to generate digits. If you have 2 or 3 layers, I couldn't find a video of it. There used to be a demo of it on the deeplearning.net. I'm not sure if it's still there. It produces digits that are a bit better than the ones from the one-layer Boltzmann machine, but are still not. It does an okay job for digits, I guess, but it doesn't do a very good job for more complicated images. The other thing that this was used for is greedy layer-wise pre-training. So if you remember, this was back in the days when people, there was this problem about training deep neural networks. If you had networks with many layers, the training often failed. Eventually, people started to use different activation functions and did batch normalization and so on. So there are many more modern techniques now to tackle this problem, but this was one of the first techniques that was used. So the idea here is you use the sigmoid function, you have a feed-forward neural network, and you're going to use the sigmoid function at each layer, and so you use this method as a kind of pre-training, right? So I do my restricted Boltzmann machine here, and then I do it here, and then I do it here. And then after I've done all this, these weights now become just the initial weights for backpropagation. So this is my initial set of weights, and then I now train the whole thing by backpropagation to do digit classification. And this gives a much better result, at least in the case with the sigmoid activations, this gives a much better result than if I had just started with random initial weights and train by backpropagation. And the reason for this, yeah, again, if we go back to this video, the reason is because this process somehow, in an unsupervised way, it creates features which are actually useful for classification and other tasks. So, you know, it creates these nice features for us at these different layers, and then the backpropagation just sort of starts with that and refines them. Okay, any questions about this? Where are we? 8:15. I think I'd like to just show you a few slides from the next topic, because it kind of ties in with this. It ties in with this quite nicely. Let me just see if I can. Which is autoencoders. So I'm just going to show you a few slides, and then we'll go through a couple of exercises, and that'll be it. Okay. So this is another way of doing this unsupervised pre-training. So you remember we talked about these encoder networks, right? So we were looking at just, I put in, well, these examples were very simple. I have a one-hot encoding, and I go to a smaller number of dimensions, and then I try to train it so that the output is equal to the input, and it forces it to kind of compress the data into a smaller dimension. So we initially looked at this just as an exercise to understand the geometry, but it is possible to do this on a more industrial scale. I can put in an image. Let's say my input is an image, and then I have a smaller number of hidden nodes, and my output is an image, and I train it so that the output should be an approximate. I train it, the target is equal to the input. It tries to recreate the input as best it can, but because it's going through a smaller number of hidden nodes, it forces it to somehow compress the information into a smaller dimensionality and then expand it out again. And this is sometimes used as a method of layer-wise pre-training. So I start with a network like this. I train this network it's unsupervised. I train it to just reproduce the inputs. But hopefully that will produce hidden unit activations, hidden features which are useful for some task. And after this is trained, I can chop off the top half of this network and replace it with some, let's say I take this layer that's already been trained, and then I add a different top layer that does a classification task, and then I can train the thing by backpropagation. So this can be used as a kind of pre-training as well, okay? So there's a lot more to the story, but I just wanted to mention that as an alternative method. We'll talk more about this after the break. Okay, let me just make a couple of remarks about, let's just have a quick look at a couple of these exercises. I won't go through all of them. All right, we'll first look at this hidden unit geometry. So this is Yeah, so this is an example of this encoder network. So I have 6 different inputs with one hot encoding, and I'm training this with these 3 outputs, and you're asked to draw a picture of what the hidden unit activations might look like. So here, this first output should be 0 for inputs 1, 2, and 3, and 1 for inputs 4, 5, and 6. So I try to put these numbers 1, 2, 3, 4, 5, 6 in a square, and this line has to divide so that 1, 2, and 3 are on one side and 4, 5, and 6 are on the other side. This second output, 3 and 6 are on one side and everything else is on the other side, and the third output, 2 and 5 are on one side and everything is on the other side. So sometimes you have to kind of manipulate these things a bit to get them in the right shape to achieve these boundaries. What else can we look at? Let's have a quick look at this image processing one. Okay, so this first thing is just an interesting example of this softmax. So we imagine that we imagine that there are 3 outputs, and the correct output is, let's say there are 3 outputs, and the network outputs 1 for the first output, 2 for the second output, and 3 for the third output. So the network is assigning a high probability to node 3, a middle and a low probability to node 1, and a sort of middle probability to the second node. So if the way this, so the probability is proportional to E to that power, right? So it's going to, E is equal to 2.718, E squared is 7.389, and E cubed is 20 point something. So the probabilities are going to be in these proportions, but we have to divide by the normalizing constant, which is the sum of all of them. And so the probabilities actually look like this. And you can see, right, so by assigning, because this is 1 bigger than that, it means that this probability is E times that. Right? So the network thinks that this should be the most likely, but in fact the correct answer is this one. And then you're asked to calculate the derivative, the differentials. So we want to increase the probability of we want to maximize the probability of the correct class. So the numerator only has an effect when we're looking at the actual correct class. So the derivative of so the derivative of the correct class has this 1 here because of the log of e to the zi is just zi. So the derivative of z2 with respect to output 2 is equal to 1. But for the other outputs, it's 0. And then you get the effect of the denominator. So it's interesting to see what happens here, right? So the correct class is, this is the correct class, but we thought that the probability was only 0.24, but the real probability should be 1. So the differential applied there is 1 minus the probability that we estimated, right? So that sort of makes sense, because if we estimated a probability close to 1, then there should be very little change, because we're getting the answer correct. if we're only estimating 0.24, then the change is 1 minus that, right? So we're increasing that output by the difference between what we estimated and 1. And then the other two outputs were the differential is equal to the negative of the probability that we estimated. So we estimated that this one was, we made a big mistake here by thinking that this had a high probability. So we're reducing it by something proportional to that high probability. This one we already assigned a low probability, so we're only reducing it a little bit. So if you think this through, there's actually is a very elegant way of adjusting the weights. And notice how there's a balance here. This is increased by a certain amount, and all the other nodes are decreased by an amount that adds up to the same amount. So there's sort of a balance there as well. Yeah. Any questions about that? Yes?
Why did we subtract the 1 in the second equation?
In the second equation, well, it's a bit hard to know how to deal with this notation, but it's the probability of the correct class. It's always the probability of the correct class that we want to maximize. And in this case, the correct class is 2. So the thing we're trying to maximize is the probability of 2, which is x of z2 divided by this denominator. So when we take the derivative of z2 with respect to zj, when j is 2, it's equal to 1, but when j is anything else, it's equal to 0. So that's why we get a 1. That's why we get this 1 here only for the correct class and not for anything else. Okay. This will be the last thing, and then we can go. So this is just a question about these. How to calculate the number of nodes in a convolutional network. So I took this. This is an actual quote from one of these papers. So the input image is 84 by 84. So there's a little bit more to this. So they're actually downsampling. I think they're scaling down the image from its original size, and they're converting it from color to black and white. And they're taking 4 consecutive frames, or four frames at very small time intervals. So the first hidden layer has 16 filters, and each filter is 8 by 8, and the stride is 4. And they don't mention any padding, so we just assume that there isn't any padding. So then how many weights are there per neuron? Well, each neuron in that layer is connected to 8 by 8. Each neuron in that layer has a receptive field of 8 by 8, and there are 4 input channels. So it's 8 times 8 times 4. If we have the bias, then we add 1. So I know in the assignment we actually didn't have the bias. Yeah, so sometimes we have the bias and sometimes we don't. Now the width and the height of the layer, so the stride is 4, so if we number those inputs from 0 to 83, the first filter will start at 0, the next one will start at 4, and then 8, and then 12, and the last one will start at 76, because the last filter it'll range from 76 up to 83, right? So the first one starts from 0, the last one starts from 76. So if you divide 76 by 4, you get 19. the answer is actually 20 because you're counting them inclusive. Right? So the next layer will be 20 by 20. So the number of neurons in the layer is 20 by 20 times the number of filters, which is 16. The number of connections is the number of neurons times the number of weights per neuron. And if we want the number of independent parameters, well, for each filter, there's 16 filters, and each filter has 257 parameters, so this is the number of independent parameters. Okay. And that's the first layer, and then you can kind of go on from there. The other layers are, it's the same kind of logic. The fully connected layer, the previous layer is 9 by 9 with 32 filters. This is the number of neurons, and then those are fully connected to 256 neurons. Okay, so you could look through you can go through the details of that. Any questions about this? Yeah. Good. Okay, so if you, like I said, the consulting sessions will still be on this week, Wednesday 4 to 5, I think it is, and Thursday 11 to 12. Or if you want to, if you need to email us or anything about the assignment, the third assignment will be released in the next few days or Monday at the latest. There's no lecture in week 10, so I'll see you again Monday of week 11 and have a good break. Yeah.